We're starting section 3.8, implicit differentiation. First we discuss implicit functions that we're talking about so much, then implicit differentiation, then derivative of logarithmic functions. So these are some of the graphs of implicit functions. You can see that none of these graphs are graphs of a function. They're actually graphs of these equations that relates x and y together. And so the other thing that to notice is for each of these graphs, you can break them down to pieces that are graphs of the function. Over here, you can have, you can go with this piece, and then you can go with the one over here, and you get two graphs two graphs of two functions. Over here, you can break it up to, I don't know, up to here, and then break and have the rest going on and down there. And same thing in here, you can have pieces that are graphs of the function, or you can have the entire thing as x graph of as x function of y instead. And here also you can break them down. Other things to notice is some of them you actually can solve for one or the other variable. And here you can solve for x, and therefore basically you can have the rule of a function x equal to again the role for x and y changes in the blue graph, and it would change in a blue graph if you solve for x and have x as a function of y. Over here you can solve for y as y. The equation is a quadratic equation in terms of y. If you take the y as the unknown variable and x to be a constant, then you can solve this quadratic equation with variable y for variable x, and same over here. In fact, that's how these two were graphed, and there this one had two pieces of graphs that are stuck together, one that is kind of lower and then the other one that is higher, and same thing here. And so, but it doesn't matter, and this one was not graphed that way, and another method was used because solving for cubic is not a cubic polynomial is not that it's more complicated than quadratic polynomials. And so whether or not you can solve the equation, as long as you have any relation that creates an equation involving x and y, basically we can regard y as a function of x, except for where the derivative doesn't exist. Even if we cannot solve for y explicitly, it is still an implicit function of x. So back again in here, there were a lot of places, even where we couldn't solve, we could still break it down into pieces that were functions, and so we can consider that as a function of x, implicit function of x, or x as an implicit function of y. Now let's when you look at a graph of a function like this, an implicit function like this, you may wonder what is the slope of the tangent line at a certain point. Let's say point -2 and 2, and that would be right there is the point. And to find that slope of the tangent line, you have to take the implicit differentiation, do the implicit differentiation. And basically, implicit differentiation is an application of the chain rule. And so the idea behind the implicit differentiation is you take the equation and you differentiate both sides of the equation. Every time you see, basically you see y, you have to remember y is a function of x, or one of the one of the two variables is the function of the other, or maybe there would be more than two variables, and you assume that all of the other ones are function of one of the variables. And then every time you do that, in derivative of inside will render a y prime of x, and then you solve for y prime of x, and you get your basically y prime, and then you enter points. And usually for implicit differentiation, you have to know both x value and y value of the point, and it gives you a slope. So let's do example 1a. The circle of radius 5 is defined by the equation x squared plus y squared equal to 25. To find y prime, first differentiate both sides of the equation. So if you're differentiating both sides of the equation, you have to remember y is a function of x. And by the way, derivative of the constant is going to be 0. So derivative of x squared is going to be 2x. Derivative of y of x to the power 2 is going to be 2y of x, y prime of x. As this one is the generalized power rule. Generalized power rule says some function to power, the derivative of that with respect to the input variable is going to be 2 times the function unchanged. It's going to be the power times the function to unchanged to a power 1 less, and then times the derivative of the function, and that's what you're getting. That's the power, this one's the power, this one is the inner function to power 1 times y prime of x. So this equation, after taking derivative, becomes 2x plus 2yx times y prime of x equal to 0. So the purpose of this is that we took the derivative and y prime appeared. So solve for y prime. Solving for y prime, adding and subtracting 2x from both sides, dividing by 2y, and that gives you, and it helps that to abbreviate. After you understood the chain rule, it helps to abbreviate. Instead of writing y of x, write y, and y prime of x, write y prime, and then solve to get y prime is equal to negative x over y. And now if you have, let's say, if you have 2 points, if you have a point on the graph of the function, why is it important to give both x and y? Why can I just give x and find y value? Look at the graph of the circle. Let's say if I give you a point 3, x equal to 3, that's example 1b. What is the slope of tangent line to the circle at x equal to 3, there are 2 points on the graph of the implicit function with x equal to 3. What are the 2 points? Plug in 3 in the equation of the circle, and you end up with 4 and -4. So 4 and -4 give you different y prime value, and they give you different slope. So 3 and 4, if you plug in here, if you plug in 3 and 4 in the derivative, then you will get, if I plug in 3 and 4 in here, let's say 3 and 4, and so, sorry, the 4 is not very obvious. If I plug in 3 and 4, I get -3 over 4, which is -3/4, right? If I plug in the other value, which is 3 and -4, then -3 over -4, the slope is going to be 3/4. So the slope is different. Also the tangent line are going to be different for the 2 points that both have x equal to 3 on the graph of implicit function. Example 2, implicit differentiation. So by viewing y as an implicit function of x, we're viewing y as a function whose formula f of x is unknown, but which we can differentiate. Implicit differentiation, again, is an application of the chain rule. So let's just remember that every time you take the derivative for the first few times until you become more familiar with it. So when you say derivative of basically derivative of y with respect to x, derivative with respect to x of y, then that's dy dx. If you are saying derivative of y to the third with respect to x, according to the general power rule, this is 3y squared, and derivative of inside, which is derivative of inside function, which is y, that would be dy dx. Now if I'm taking derivative of with respect to x of e to the power y, again, it's the chain rule. The outside function is e to the power u, and so that would be e to the power u again, so e to the power y, but you have to take the derivative of inside function, that's dy dx. Now the product and quotient rule will still apply. If you're taking derivative of x times y, first you get the first function times the derivative of second function, so it's x times dy dx. Then you get derivative of first function, which is 1, times second function y. What about when quotient rule? Quotient rule again applies. Derivative with respect to x of x over y is going to be the derivative of top, which is 1, times the bottom, which is y, minus the high, which is x, times the derivative of bottom, which is going to be dy dx over y prime again, divided by y to power 2, which is the denominator. How about derivative with respect to x of x squared, y squared? That is going to be, again, a product rule. It's going to be the first function, x squared, times the derivative of y squared, second function. And derivative of y squared is a generalized chain rule, 2y, y prime. Then plus derivative of the first function, 2x, times the second function, y squared. Another quotient rule, derivative respect to x of x plus 1 over y plus 1 is going to be the denominator, which is y plus 1, times derivative of numerator, which is 1, minus the numerator, x plus 1, times the derivative of denominator. What is derivative of denominator? Derivative of y is y prime, derivative of 1 is 0. So it's y prime. Divided by the denominator to power 2, which is y plus 1 to power 2. And so these happen over and over and over again. What is recommended is to try to do this on your own a few times and make sure that you understand the steps, so when you see them in basically more complex problems, you don't miss this step. I click here, question 1. Find dy dx implicitly if y cubed is equal to x squared plus 1. Okay, this is an implicit function again. Now, the options are A, derivative of y with respect to x is 2x over 3. B, derivative of y with respect to x is 2x over 3y squared. C, derivative of y with respect to x is 0. D, derivative of y with respect to x is equal to x squared plus 1 over 3y squared. E, derivative of y with respect to x does not exist. So pause and answer and come back. And now, if I want to take the derivative implicitly, derivative of y to the third is a generalized power rule. It's going to be 3y squared times y prime. Derivative of x squared is 2x. Derivative of 1 is 0. So y prime is going to be equal to, now solve for y prime, and it would be 2x divided by the coefficient of y prime, which is 3y squared. And that is B.